Alright, so this is an introduction to acids and bases, which you should have had a pretty good introduction last year in Honors Chem. Key things: acids, you taste sour, you like in a citrus, citrus products or citrus, like oranges and lemons have large amounts of acid, so they taste sour. They feel like water if they're on your hands. They're good electrolytes. We remember that from chapter 4. They turn blue litmus paper pink, and their pH is less than 7. So those are common properties of acids that you should know. Bases taste bitter, like example is soap. If you ever had soap in your mouth, let's say you say a cuss word and your parents put soap in your mouth, the soap would have tasted bitter. They feel slippery when they're on your hand. They are good electrolytes as well as strong acids. They turn litmus paper blue, and their pH is greater than 7. So those are some fundamental properties of acids. An Arrhenius acid, we say, is anything that breaks off and produces H plus ions in solution. That's the simplest definition of an Arrhenius acid. So like HCl, like right here, the H is going to break off and you're going to get H plus and Cl minus. That's the simplest definition of an acid. The one we use most often in AP is Bronsted-Lowry. Bronsted-Lowry are acids that are substances that donate, Bronsted-Lowry acids donate H plus ions. Really what it means is, this is the key thing, they lose NH. So going from left to right in a reaction, it's going to lose one single H in a Bronsted-Lowry reaction. Bronsted-Lowry acid-base reaction. The last definition of acids, there's 3 kinds really in chemistry. We don't use the Lewis too often. It's something that accepts an electron pair, but we'll deal with that later. I'm not going to really get into it too much now. The definition of a base. Arrhenius definition of a base means it has OH ions. So for example, something like lithium hydroxide. How do you know it's an Arrhenius base? It's pretty obvious because you can see the OH and you know it's going to break apart. But the problem with that definition of a base is it didn't cover some of the things we knew that were basic. For example, ammonia is NH3. We know ammonia is a base, but it lacks an OH, or a hydroxide group. So Bronsted-Lowry's definition is better for us because it says bases are substances that accept H plus ions from other substances. So basically what that means is they gain an H. That's what you really want to focus on. Remember I showed you acids earlier. We said acids lose an H according to Bronsted-Lowry, and now we're saying that bases gain an H according to Bronsted-Lowry. Lewis' definition of a base is something that basically donates electrons, but I'm not really that concerned about it right now. All right, conjugate acid-base pairs. When you go to find Bronsted-Lowry, key thing you have to be able to do in AP is determine who is the Bronsted-Lowry, who is a Bronsted-Lowry acid and base. So what I do is I look here. This is this species on this side, and here it is over here. It contains the same ion. What's the difference? Here it has one H. When you go over here, it lost an H. So going from left to right, I would label this as an acid according to Bronsted-Lowry. This is going to be an acid because it loses an H. Loses an H going from left to right. So that's my Bronsted-Lowry acid. Well, if we keep track of this one over here, we got water here, and it turns into H3O+. If you notice, the total number of H's it has is 2 here. It goes up to 3 there. Because the whole thing with Bronsted-Lowry is you're trying to track down one single H. That's it. So if you look right here, it goes from 2 H's to 3 H's. So Bronsted-Lowry would classify that as a base. The other thing we do in chemistry is we do conjugate acids and bases. That's like if you take the reaction and you reverse it. So if you start on this side, I have 0 H's. There's no H's there. When I go back the other way, I gain an H. So we're going to say that's a conjugate base because in the reverse reaction it gains an H. Same thing with this species right here, H3O+. I have 3 H's, and then on the reverse reaction it goes from 3 to 2. That makes that a conjugate acid because a acid, according to Bronsted-Lowry, loses an H. Go down to this reaction right here. I start here, and here's the matching species on the other side. Remember, the only difference in all these reactions is going to be a single H. How many H's do I have here? I have 0 H's. How many H's do I have here? I have 1 H. So it went from 0 to 1. That's going to make that a Bronsted-Lowry base. When I look at the other species, HCO3 to CO3 2-. What's going to happen here? Well, If I look, to start with, I have 1 H. On the other side, I have 0. So what does that mean? I go from 1 to 0. According to Bronsted-Lowry, that's going to make that an acid. That'll be classified as an acid. If I reverse it or flip it over, this goes from 0 to 1. That makes that a conjugate base. That's a conjugate acid. So there you go. When you're doing Bronsted-Lowry, conjugate acid, conjugate base, you're looking for the H. Fundamentally, an acid always loses an H. A base always gains an H. Here's another couple. We'll do one more of these. If you look right here, starting here, 0 H's, 1. So it goes from 0 to 1. That's going to make that a base. Gains an H. This starts out as 2 H's on this side, ends up with only 1 on that side. If you go from 2 to 1, that's going to make you an acid according to Bronsted-Lowry. This will be my conjugate base, conjugate acid. So you get the idea as far as conjugate acid, conjugate bases. Definitions. One of the things we talked about in chapter 4 is a acid strength. Acids disassociate. When it disassociates completely breaks up, it is a strong acid, and we say it has a large equilibrium constant for an acid. We call it Ka. It has a subscript A for acid. It has a large ionization constant, so large that we don't even classify it. We just say it's huge, it's large. It is extremely good electrolyte because it breaks up completely. HCl is considered a strong acid. It completely breaks up into H3O plus and Cl minus. So the fundamental definition of a strong acid is that it completely dissociates. That's the fundamental key thing you need to know about a strong acid. So if you look right here, here's an example. We say this thing is HA is a strong acid. So if you start with this much, it has 100% dissociation. It breaks into H3O plus or H plus, which makes up an acid, and it's ion without the H. A weak acid, on the other hand, only partially dissociates. So only a little piece of it's going to break up. So when a weak acid breaks up, it's only a little piece. So if you notice, you get a little bit of H plus and a little bit of the other ion. A very weak acid, almost close to 0% dissociation. It barely breaks up at all. All right. Common weak acids. There's a lot of common weak acids. First way you tell a weak acid is it's not one of the strong, 6 strong, which you have to have memorized. You had to memorize them in the summer. There's a Quizlet. If you don't know, you can go back through and memorize them because I will ask you tomorrow. Hydrofluoric acid is a common weak acid. If it has a Ka value, automatically pretty much makes it a weak acid. So if you look, but these are not the strong acids. They're not listed as strong acids on our sheet, on a chart, or in our cards. So that's how we know they're weak acids. How do we rank these according to strength? We do it by the Ka value. The larger the number for this Ka value right here, larger the Ka, the stronger the acid. So the larger the Ka value, the stronger the acid. So if you go here, if you look right here, Ka values, if you notice, this acid has the highest Ka value, therefore this would be the strongest. As you go this way from the bottom of the table to the top, notice acid strength increases as the value of the Ka increases. The equilibrium constant for the acid known as Ka. All right, pH scale. You guys probably learned about this in middle school. H plus, acids produce H plus ions in solution. So with the way we determine pH, the pH scale is based on the amount of H plus. So the thing that determines pH is the amount of H plus or H3O plus. It's basically the same thing. You can write it either way. That means the same idea. pH is basically found by taking the molarity, notice the brackets, of whatever the H3O plus is, you take the negative log of it. Negative log of it will give you the pH of a substance. So you guys probably had to do this last year, probably had to do it several different years in science, and that's all pH is the concentration of H3O plus. The negative log of it will get you pH. For example, if you take H3O plus, which has a value of 0.01, you take the negative log of that, you get a pH of 2.0. We place those values on a scale. Here's our pH scale. If you notice, anything that's 7 is considered neutral. Anything that is below 7 is considered an acid. And as the pH gets lower and lower, it becomes more of an acid. Anything that is above 7 is considered a base. And you can see some household items, bleach, Milk and magnesia. You look on the other side, coffee, tomatoes, wine, vinegar. Those are examples of acids and bases. All right, what does it really mean when we say something's acidic or basic? When something's neutral, first of all, like water, it means the concentration of H3O plus and OH minus hydroxide and OH are equal to each other. That's what a neutral solution is. They cancel each other out. When you say something's an acid, what it fundamentally means is that you have more H3O plus than OH minus. So the ratio, this is higher, therefore it will give you a higher pH value. A basic solution is the exact opposite. A basic solution means you have more hydroxide than H3O plus. All right, a couple other key things you need to know, vocabulary for this chapter. Polyprotic. Protic refers to H plus or H3O plus, which is a proton. Poly means many. Polyprotic acids mean that you have more than one H. Monoprotic acids, as you see right here, like HF, HCl, HNO3, they only have one H that breaks off. A diprotic acid, di means two, H2SO4, H2CO3, those are considered diprotic acids. And if you notice sulfuric acid, we say that those acids dissociate stepwise. One H comes off at a time. So if we have to write out the Bronsted-Lowry reaction, what we do is we take one of these H's, we give it to water, so you get H3O plus, and then this is missing one H. You have the HSO4 minus. That becomes a reactant in the second equation. Then it gives another H to water, making H3O plus. Once you take the H off there, you end up with SO4 2 minus. So when we talk about polyprotic acids or a diprotic acid, we assume that the H's come off one at a time. Amphoteric. You'll hear that every now and then in the chapter. Amphoteric refers to the ability which can either act as an acid or a base according to Bronsted-Lowry. What that means is you can either lose an H or gain an H. That's what amphoteric means. So you have the ability to either gain an H or lose an H. So if you look, water is an amphoteric substance. If you look here, in this case, water takes an H from HNO3 and becomes H3O plus. So in this equation, it's acting as a Bronsted-Lowry acid. You look at the bottom equation, you have two H's on this side, and you have one H on this side. It transfers an H to NH3, making NH4, and then OH minus. In this case, it acts as a, whoops, it's acting as a base up here. Nice job, Davis. This is actually a base. I mislabeled it. This is a base because it goes from two H's to three H's. This is a Bronsted-Lowry acid because it goes from two H's to one H. So remember, acids lose H's, bases gain. So in this equation, you see water is a Bronsted-Lowry base. This equation, you see water is a Bronsted-Lowry acid. To be amphoteric, a substance basically has to have a hydrogen ion to donate, and it's usually, with the exception of water, negatively charged, because in order to tack another H on, it has to be able to cancel out a negative charge. So to find something that's amphoteric, two things. It's got to have an H to give if it's going to be an acid. To be a base, it has to have the ability to accept an H, which means it usually has to be a negative value. Make sure you go through and study the review sheet. That way you do well on the little quiz we have tomorrow. And we're going to get started with Chapter 14. Bam. Have a good night. I'll see you tomorrow.